It's working, huh? Yes, it was on YouTube. I have to send to my parents, they will be very proud. But I realized that on Monday, it started to look here. I was very, very disappointed. Because it's very difficult for me to look. I'm not used to look on the mirror. Yesterday it was better, so today I have to. Okay. But the quality is very good with respect to the past ones. I mean, for the last years. It's nice because it's just the head, no? It's moving the head up and down. Okay. So yesterday we concluded with the first kind of approximation, since as you may remember, the equations are pretty difficult to be solved, both for the air and for the seawater. So what people usually do is to apply some sort of approximation. So the first one, and this approximation, as I told yesterday, are basically derived from observation. So how GFD phenomena actually occur in on our Earth. So the first approximation is based on the fact that density can be written as a mean value, a background value, rho 0, and a perturbation, density perturbation, rho prime, which is actually depending on space and time. And what we saw yesterday is that if we apply and we make a reason on the continuity equation, we obtain something like this. Okay, so a divergence-free flow. So this is actually very useful. And we use practically to reach this point. We use some sort of scale analysis. So we analyzed the different terms of the equation. In on the book by Cushman, you will find slightly different approach, but more or less it's the same. Okay, so you can do it as we did yesterday. So just by looking at the equation of state of the seawater, which is a specific case. But we can also remember that usually space and time variation in density are much smaller than space and time variation in velocity. Okay, relative, of course. Okay, so let's look at what happened to the other equation, to the momentum equation. So for example, the X momentum. So we wrote yesterday the X momentum, du over dt, and then we have the two terms coming from the Coriolis force, and then we have the gradient of pressure along X plus the three terms of the stress tensor, where tau Ej is equal to mu, which is, do you remember the name of this constant? Mu. There are two kinds. Sorry? Lambda, it's another one. No, you were not close so far. It's the viscosity, but there are two kinds of viscosity. There is dynamic viscosity. Then we will talk about the kinematic viscosity. So, dij plus djy. Okay? So we want to see how actually the stress tensor tells you which is the shear, okay, along the three direction applied to the three velocity component in general. Okay, so remember our approximation. So what we can do here is to simply substitute rho as the sum of rho 0 plus rho prime. This remains the same. This remains the same. What happened here? So let's start to look at this term. So we have dx of tau xx, which is mu dxu plus dxu plus dy mu. So it's tau xy, so dxv plus dyu plus dz mu dxw plus dzv. Okay? Easy.
Shouldn't was that one y?
Sorry?
There, dxu plus dxu.
I don't understand. This one?
Yeah, there.
So it's dxu plus dxu because it's x.
Okay.
Okay, I is equal to j in this case. Okay, so let's look a little bit this one. So we can, mu is a constant, so put it outside from the parentheses. So we have a second derivative of x plus, again, second derivative of x. Then we have a mixed derivative xy v plus second derivative of u with respect to y. And then we have the xzw plus second derivative of u with respect to z. Okay? So we have 1, 2, and 3 second derivative applied to u. And then we can, so this term here can be written like Laplacian of u, okay, so, or gradient of gradient, as you want to look, but Laplacian. And then we can write dx and express this as dxu, so we can put in evidence, gather together the x derivative. So we have dxu plus here we have dyv, and here we have dzw. Okay? So how much is this?
0.
Is 0. Because we know that we are working with non-divergent flow. So the result is that we have just this term here. Okay? So here we can neglect rho prime because we know that rho prime is much smaller than rho 0. Just remember that we cannot do it when we have the gravitational acceleration. So at the end, we maintain this form here with rho 0. Okay? Similar, exactly the same we have with the v component, so the y component of the momentum. So we will have rho 0 dv dt plus fu, which will be equal to dp dy plus mu Laplacian of v. Okay? So this term here is the term that taking account the dissipation. Okay? Friction, dissipation due to friction. With mu as a constant, which is dynamic viscosity. we can do a little bit more, and we can divide everything by rho 0. So simply what we have here will be only the part related, let's say, left-hand side of U, left-hand side of V, and then we will have just minus 1 over rho 0 dxp, and here when we have mu over rho 0, we have the kinematic viscosity nu. Okay, don't confound nu and mu. And here is the same. Okay, good. So not so much, but at least a little bit. All the terms related to the stress practically has been reduced to a simple diffusion. Simple is a big word because, of course, we are still working with the second derivative differential equation. So, mathematically speaking, it is not so easy. Okay, let's now have a look at what happened to the z component of the momentum. So z component of the momentum is not symmetric, not similar like u and v, because we have rho dw dt, then we have here plus f star. F star u minus dt z. Then we have the same thing here, of course, with the zx, zy, and zz. And then we have rho g. Okay? So, for this, I am pretty confident to say that we will obtain exactly the same form as before. Okay? But now we have to take in account this one. So, what happens if we substitute to rho 0 and rho prime? So, what we have here is rho 0 plus rho prime. So, we cannot say, okay, rho 0 is larger than rho prime, and we can neglect it. Don't do it. So, here we can do it. But there is another thing that we have to look at, is the pressure. So exactly like the density, we have to take into account the effect of the hydrostatic pressure. Okay? So hydrostatic pressure basically is defined on the fact that we have the total variation. So hydrostatic pressure only depends on the vertical, because hydrostatic pressure is nothing more than the effect of the weight of the fluid over the pressure. Okay? So it's simply equal to this one. Okay? So this is the equation that rules the hydrostatic pressure. So the variation of the hydrostatic pressure with respect to z is nothing more than equal to the coefficient is relative to the weight of the fluid. Okay? So this means that we can write P as P0 z plus P prime x, y, z, and t. Okay? So we apply the same point of view of the Boussinesq equation also to the pressure field. And we divide the pressure field in a term which is only related to z, so it's related to the hydrostatic component, and the other one which is a sort of, again, a perturbation of the pressure field. Okay? So, if we integrate this expression here from a certain level z0 to a certain height z, so let's for example, think to be in the atmosphere, what we will have is the expression of Pz, which is equal to, we will call it a capital P0, which is a reference pressure, okay? It's just the integration constant, nothing more than that, minus ρ0 Gz, okay? So this is the expression of the hydrostatic pressure, which actually tells you that if we put Z here and the pressure here, so this will be my reference pressure at Z equal to 0, which is actually the surface pressure at the sea level, if you like. Okay, so any kind of reference, or it can be, for example, the pressure at 1,000 meter depth in the ocean. And of course, as we go up in the height in atmosphere, or we go shallow from the depth of the ocean, of course the pressure is reduced because we have less and less fluid here. Okay, when we are here in Trieste at the level of sea level, we have a column of air above our head, which is about 10 kilometers high, more or less. Okay, so you can, for example, to understand, it's a nice exercise to understand how much is the weight that every of us, our body is able to support, is that you have to integrate all the mass that you have over your head. Okay, of course, if you have, if you are in Nepal, the pressure is much lighter, so people are a little bit more relaxed. Okay. Less stress. Okay. In the ocean, of course, since the density is 3 orders of magnitude larger, it's enough to go deep 10 meters to obtain the same pressure that you have in the double the pressure that you have on the surface. Okay. So with this new expression that I report here, we can come back to our equation. So we have here ρ0. So this P is nothing more than this one. Oh, of course, sorry, is P is equal to Z plus P prime. Okay? So we have to make the derivative of Pz plus P prime. Then we have this one, and then we have these two terms here. Okay? So the first derivation can be directly written as a total derivative because P is only dependent on Z. But we know how much the P on the Z because we had the expression before. So if we do the P on the Z, we have just minus ρ0 G. Okay? Then we apply this one to the P prime. Okay? So this term here has become this one. Now, what we can do, since we have a minus here, so, right? Okay? So we have minus plus, and this is neglected. Okay? So what we obtain, we can again divide by ρ0. What we have here will be 1 over, not Zx, but Z. 1 over ρ0, this will be nu, and this will be just ρ prime. Just G, sorry. Okay, so Now we are working with a little bit too many variables. So what we will do, since we can be quite safe to avoid any kind of confusion, we will always refer as rho as the rho prime, okay, so neglect the prime, and as p as the p prime here, okay, which we call dynamic pressure. So what would it mean? It means that when we have here the p and the px and also the py in the two horizontal momentum components, since the hydrostatic pressure is only dependent on z, we know that we only have the p prime, okay? That with the simplification of notation, it simply will become the p, okay? So from now on, if not specified, when we will see rho, it will be the rho prime. So the variation, which is the only important thing, because rho 0 is just a constant, and p will be the p prime, which is the perturbation to the yeah. Okay, good. Well, we can do something more similar also to the energy equation, but the energy equation we can also look at here. Energy equation, both for air and for seawater, you see that we have the term related to the divergence of the fluid, okay? So what happened that for the seawater and for the air, this term can be neglected. So what we have is just dt over dt, so the time derivative of temperature, which is equal to its diffusion. So the energy equation actually become a diffusion equation of the temperature. And we can even take in account the equation of, so we have rho Cv dt dt, which is equal to k Laplacian of T. So this was the heat conducibility, okay? This is the density. Of course, here is rho 0. We can do it quite directly without thinking too much. This is a constant, of course. So we can have one new constant, which is k over rho 0 Cv, which is called the heat diffusivity. So similar thing we can do also for the salinity, for the seawater. So we will have two equations, T kt and ds T. Okay, so the two equations are actually isomorphic. So this is our original energy equation, but if you remember, we can put all together using our equation of state, okay? So if we play a little bit with this one, nothing very difficult, so we can, don't forget that this is the total, okay? So it's not, in this case, this is the total, so don't be, this was the previous way to write. But we can quite easily represent this as rho minus rho 0, okay? Which is equal to minus alpha T minus T0 plus beta S minus S0. And this is our rho prime, okay? Because is rho minus rho 0. Okay? So if we put here the operation of a total derivative and we act with the same here, what we will have here is that this operator, of course, we will have the t over the t and the s over the dt.
Professor, there's a row zero remark.
Yes, you're right. Okay. So the t over the t, the s over the t, we can use the two diffusion equation, and what we obtain is that we can found a new equation which is this one. Okay? So from some thanks to the Boussinesq approximation, we were able to put together the equation of the energy and the equation of state in one single equation. Okay? Don't forget that we still have to keep this one, but at least we have saved one equation. Okay. Yes. So there is another series of approximation which still come from the observation of GFD phenomena, and again is related to the scales of motion. So if we look at the typical scale of atmospheric and oceanic flow, we already looked at that in the yesterday and also on Monday. So we must be able to play with this number. Okay, so every kind of variable of our equation, so x, y, z, time, the tree velocity, pressure, and rho, which is now variation of density, can be represented by a scale. Scale is, as we said Monday, is like a sort of order of magnitude of that variable. Okay? And of course, this is the unit. And we can have atmospheric value and oceanic value typical of our system. So if you remember, we have the typical atmospheric value for horizontal dimension is 100 kilometers, and while the oceanic value is one order less. For the height, we have 1 kilometers, while for the oceanic value we have 100 meters. For time, we have half a day and 1 day. For horizontal velocity, 10 meters per second and 0.1 meter per second. So most of them, there is one or more order of magnitude of difference between atmosphere and ocean. Also, we can add, okay, for what concerns the vertical velocity, it is very difficult, very, very difficult. Vertical velocity is very small, very difficult to measure vertical velocity actually. So, by the way, they will be, as we will see, very, very smaller with respect to the horizontal one. And finally, we have that the variation of density is 1% or 1 per thousand of the background density. So, using this expression here and recalling what we looked last days, that the typical time scale are larger than the scale of rotation, or also that the scale of rotation, the frequency of rotation is larger than the frequency of the motions, and also that the horizontal dimension are much larger than the vertical dimension. Okay? So if you think, for example, to our Earth, so we have that the radius is, do you remember how much is the radius of this?
6,371.
Very good. One prize for you. Okay, so how much is the typical height of atmosphere? 1 kilometer. How much is the typical height of ocean? 100 meter, so 1/10 kilometer. So all the GFD is living actually on a peel of a little bit more than 1 kilometer. Let's say we can extend, of course, to 10 kilometers, for example, here, and to 5 kilometers, for example, here. If you want to take the entire troposphere and let's say the average depth of the ocean, of the global ocean. So, okay, let's say 15 kilometers. Okay, how much is 15 kilometers over 6,371 kilometers? It's very. It's like 1 millimeter over 1 meter. So take a ball of 1 meter of radius, so 2 meters of diameter, and put one foil of paper, one sheet of paper. So this is the dimension of our atmosphere and our ocean over the Earth. Okay? So that's why if we want to understand how the motion are occurring, it's quite good to consider this approximation. So with these numbers and with this new simplification, we can further have some ideas from our equation. So let's start from the continuity. So we have du over dx plus dv over dy plus dw over dz, which is equal to 0. So now we will do the scale analysis. Okay? So what is the scale of u? Just tell me, don't consider this one, just look at this. We are variable u, small, so the scale is capital U. Okay? How much is the scale of x? L. Then we have, again, u over L, and here we have w over h. Okay? So these three terms should balance, okay, because this is what our equation says. So let's try to see how they can be put one with respect to each other. So, for example, the first case, would it be possible that this vertical divergence or convergence? So now we'll start to use a lot this word, divergence or convergence. So this is telling you how much the vertical velocity is changing on the vertical. And this is going to tell you how much the horizontal velocity is changing on the horizontal. So if this is correct, this means that these two terms here can be neglected with respect to this one. So it means that our continuity equation reduces just to this. But what does this mean? This means that W must be constant. Okay? So the vertical velocity is constant. Is it possible? So is it possible that for any value of z in the atmosphere and the ocean, we have that the vertical velocity is constant? If it is 0, there is no problem. It's trivial. Everything is 0. 0 equal to 0. But it is not to 0. It is a value. So could be, according to you. No, I see a lot of people saying no.
But could
Why?
it be a function of x and y?
It could be. It could be. But we are looking exactly on the variation over z. Exactly. It is possible. We have just to make the same reasoning but on different positions. So why, according to you, cannot be? So what is one of the characteristic of GFD? So we are always talking about ocean and atmosphere.
You go up, whether it's in the ocean or the surface.
You go up, yes.
Pressure also decreases.
Yeah, that's correct. So what does it mean? So if I am on the Earth, think about the wind flow.
Okay.
Okay, so what happens when we are exactly at the ground?
And there's friction, so...
There is friction. Okay, so what does it mean? If, in reality, if I take a measurement, okay, so I have like trees, and I have like here, let's say an wind measurement. Okay, so I will see here, let's say 10 meters per second. Okay, what can I measure here exactly at the ground? Zero. Zero, exactly. So it means that this velocity must decrease with density. But if we have the conservation of mass, is it possible to have here a vertical velocity coming from nothing to a value which is different from zero? No. So because of the presence of boundaries, so we have solid boundaries. Air have boundaries on the ground, of course, and then at the end of the troposphere, because there is a change in the thermodynamic properties of the atmosphere, and the ocean has boundary because we are passing, there is a big discontinuity in density at the surface of the ocean, and then we have the sea bottom. So at the boundaries, we have that, let's say, boundary layers, that the vertical velocity must be zero, because otherwise we could not have any kind of conservation of mass. So if it is zero, so it means that this is zero, or of course cannot be constant. So this is not possible. What about the other two possibilities? So the other two possibilities are that the horizontal divergence or convergence is much larger than the vertical ones. So it means that we will have a balance based on this one. Any problem with that? No, exactly. We can have something like this. So for example, we can have, no, not like this, sorry. System like this, okay? So think about to have a sort of obstacle. So on the horizontal plane, we can have this kind of horizontal divergence or convergence. Divergence in this case, or convergence in other case. We can also have the third case, that U over L is of the same order of W over H, which is okay. We can have exactly the same thing, like, for example, this one, okay? So we have on the horizontal plane convergence, and on the vertical plane divergence. This is completely correct. It's a case of 3D divergence or convergence. Okay, so at the end, what we obtain is that U over L is larger or even more larger, or say of the same order of W over H, which means that U is larger or of the same order of L over H multiplied by W. But how much is L over H? L over H is a number much larger than 1. So it means that U is much larger than W, which is something that we can hypothesize from intuition, but here is a little bit more solid, okay? So we can also add here, like that. Okay? So let's look now at the equation of momentum. So again, let's start with the x momentum equation. So now it's important to, up to now we always considered the total derivative of the velocity. Now it's time to expand and to consider the local time derivative and the advection term. So we have du over t plus u du over dx plus v du over dy plus w du over dz. Then we have the Coriolis term. Then we have pressure gradient. And then we can expand the Laplacian okay? So, again, scale analysis. We have u over t, good. Now, what we have? U dx.
Yes.
U
squared.
U squared over L. Good. What we have here? V du dy over L. What we have? W du dz.
W over U over
Okay. F. Which is the scale of F? Omega. So this is omega W and this is omega U. Here we have P rho 0 L. And here it's nu. Then we have U over L squared, nu over L squared, and nu U over H squared. Okay, so in this moment, I open a parenthesis because on the Cushman you will find not a chapter, is the first section of the third chapter, I think, which is related to the Reynolds averaging. Okay, does any of you knows about that? Okay, you too, possibly. Okay, Reynolds averaging is nothing more very difficult. So it's based on the fact that exactly like in the Business approximation, we can we can write every kind of our velocity component as the sum of a, let's say, mean component plus a turbulent component. Okay, so the mathematical derivation of Reynolds averaged Navier-Stokes equation, which also called RANS, is very easy, not so much difficult. So you can follow it on the book. It is not part of the course, but it's important that you know about it. Especially because at the end of this, you will find the definition of the eddy viscosity. So what is eddy viscosity, which I use the letter E over the term mu. So it means that this term here, if we follow our argument, are actually the molecular viscosity. Okay, so they are related to the fluid, which is water or air in our case. But when we apply the Reynolds averaging, which is, let's say, another kind of, it's not a simplification, but it's a sort of clarification of the fact that the role of turbulence within the GFD is extremely important. What we will have is that this term here will be actually substituted by the eddy viscosity. And eddy viscosity is a flow property. Okay? Don't forget, very important. Viscosity, kinematic viscosity mu is a property of the fluid, inherently related to the characteristic of the fluid. The eddy viscosity is a property of the flow, okay? So, why? Because it is related to correlation. So with this expression here, I intend averaging, the operation of averaging. So the correlation between velocity perturbation in the horizontal and velocity perturbation in the vertical, okay? Similar, we will have also the eddy diffusivity, okay, Ka. What is the important thing to remember is that eddy viscosity is much larger than than kinematic viscosity, okay? So that's why we can quite easily, in this case, substitute the eddy viscosity in our equation. One more thing is also to substitute to the horizontal expression another constant, which is the horizontal eddy viscosity, in order to differentiate the horizontal diffusion by the vertical diffusion, which is related to this fact here, okay? The fact that we are working with the flow which are basically 2D, where the horizontal dimension is much larger than the vertical one, and the horizontal velocity is much larger than the vertical one, okay? So don't be lost, read the section, and everything will be fine. Okay, so what we can do to simplify this expression? The first thing, which was already anticipated yesterday, is that since U is much larger than W, the two Coriolis term, actually I can neglect the first one.
So, the viscosity is much larger than the kinematic viscosity. But why are you just replacing this?
Okay, because usually if you do all the analysis with the Reynolds averaging, what obtained is that you will have something like this. Okay? And this is basically related to this kind of term here. Okay? That's why this, the expression, is something related to expression like this with the minus. Okay? So that's why I told you that eddy viscosity is a property of the flow, because it's related to the correlation between the turbulent component and the mean shear of the fluid. Okay? And if we take measurement, I mean, if we are able to measure, which is not very easy, as I told you, these two components, and we calculate this, we will have that the eddy viscosity will have like value about from 10 to the minus 2, can be even 10 meters squared per second. While, do you remember how much is the kinematic viscosity for the water or for the air? Is 10 to the minus 6 or 10 to the minus 5. Okay? So that's why, again, still working on the idea of simplifying, I can, in some sense, neglect this. Okay? This is something which is very important in numerical modeling. Okay? Especially the adoption of different constant, viscosity constant and diffusivity constant for the horizontal and for the vertical terms. Okay, so another thing we can do here, just don't, for this moment, don't consider this. Since L is much larger than H, of course, these two terms can be neglected with respect to this one, okay? Because they will be much smaller than this one, okay? If we put A, actually, A is much larger than the vertical eddy viscosity, so this term can be kept. Okay, but for our purposes in this moment, considering large scale flows, we can neglect. So what happened is that we keep most of the terms except this one and these two. Okay? A similar analysis can be done for the V component, for the Y component, so it will be exactly the same. And of course, as before, we can have a little bit more, more in-depth analysis of the Z component of the momentum. So, so we have dw dt plus u dw dx plus v dw dy plus w dw dz plus minus f star u equal 1 over 0 dp dz minus g rho 0 plus nu. So in this moment I will write nu or nui. I mean, it's not a problem. It's important that you quote the concept. So we have the w squared plus dy Okay, again, so what is the first scale? W over
T.
Here,
U,
UW over
H.
L. L. X. Here,
U,
over L. Here.
Omega U.
Okay. This is P rho 0 H. This is G. We can use delta rho 0. And this is again nu W L squared. The same. And nu W H squared. Okay, so we can still use the same and neglect the horizontal diffusion. And so now we have to work a little bit on the first, on the left-hand side. So we know that U is much larger than W. So it means that omega U will be much larger than omega W. But we know that omega is larger than 1 over T. So it's okay? So it means that omega U is much larger than omega T, WT. So it means that the Coriolis terms, according to our scale analysis, is much larger than the local variation of vertical velocity. Okay? So vertical velocity can be neglected with respect to Coriolis acceleration. Okay, then we know that U over L is much smaller, not much smaller, is smaller than omega. So we can also say that UW over L will be smaller than omega W. So I just multiply by by W. Okay, but omega W is much smaller than omega U. So the third advection, horizontal advection term can be neglected again with respect to the Coriolis. Then we know that W from the continuity equation is smaller than H over LU. So it means that the vertical velocity scales like the ratio of the vertical with respect to the horizontal dimension multiplied by u. Okay, it's a sort of proportionality. Okay, where this term here is much smaller than 1. So look a bit at this one. So it means that w squared over h, so I multiply here by w and divide by h, will be less that, so we will have w u over l. But w u over l, I know that u over l is smaller than omega. So this is u, omega w, because u over l is smaller than omega, multiplied by w. And again, this is much smaller than omega u. So again, all these three terms, so all the variation in time of the vertical velocity, we are talking about the vertical velocity, is much smaller than the Coriolis acceleration. Okay? So from this, we are starting to understand that Coriolis acceleration has a very central role in our GFD, because it's important. I mean, rotation is really an important player in GFD. Okay, so it looks like our left-hand side has been reduced only to this one. Let's look now to what happened on the right-hand side. So if we calculate the ratio between the Coriolis term and the buoyancy term, okay, we can call it buoyancy, and we use those terms here, you will see that this is actually quite smaller than 1. Okay, so just a sort of mathematical exercise, just take all the value. Do you remember the value of omega?
Yeah, so 0.27 times the rest negative 5.
Double 5. Wow. Come on! Okay, so we can neglect this one. So we have that all the left-hand side is become 0, and we remain with these three terms on the right-hand side. So let's look to this term here. So okay, we can say that nu w over h squared is much smaller than nu u h squared, okay? Because w is much smaller than u. But if again I take the ratio between okay, the Coriolis term, so we will see now. Trust me, but you can also make the exercise. But you will see that if we are far from boundary layers, okay, so our flow, wind or current, is not feeling the ground, okay, we can say that the vertical friction related to the horizontal velocity is actually smaller, or even much smaller than the Coriolis. Okay? And this is related to a dimensional number that is called the Acma number. And you see, I don't think, well, maybe today, but most precisely tomorrow and after tomorrow. Okay, so if this is smaller than this, and we already have demonstrated that the Coriolis term is much smaller than the buoyancy term, we can also neglect this one. Wow! What happened? We happened that our Z momentum has reduced only to these two terms. Okay? This is very important because this is exactly the same relation that we have for the hydrostatic. So it means that even the dynamic pressure, when we look at its variation along Z, is in hydrostatic balance with the buoyancy term. Okay? So, large-scale geophysical flows, says Cushman, tend to be fully hydrostatic even in the presence of substantial motion. This is very, very interesting and very nice. Very useful also. So, last equation, the fifth equation is the energy equation. Energy equation, you remember, is nothing more than total derivative of density. So it's a diffusion of density. So we can work a little bit also to this part here, and what we will obtain is that this will be just the vertical term. Okay?
Excuse me, Professor. Why aren't you expressing the G in terms of the scales?
G is a constant. G is a number. It's like omega. So we have G and omega, which are parameter of our planet. So you can do all these things for any kind of planet. You can play taking Mars, or taking Jupiter, or Mercury, or Venus. Okay, there are many. And you change G and sigma and omega, and look what happened. These are just constant. Okay, it's like the eddy, the molecular viscosity, or the heat conductibility, or the heat diffusivity for the molecular point of view. Not these, okay? These are not, these are function, okay? But these two don't need any scale. Okay, so yes, we can finalize our effort with what we call primitive equation of GFD, which actually are the equation that you can find in the numerical models. So X momentum, Y momentum, Z momentum, where simply I was neglected rho zero, continuity and energy, okay? Where in this particular case, they also neglected you can also add here also the horizontal diffusion, okay? But what they did in this case is to give a slightly more, let's say, precise definition of the eddy viscosity and diffusivity, where in this case they depend on Z. Okay, so eddy diffusivity and eddy viscosity actually are one of the most difficult topic in earth sciences. Okay, finding a model for this one, because what happened? The Reynolds averaging actually is related to the fact that when you integrate your equation on a model, usually, first approximation, okay, there are many different recipes, but usually people discretize the volume in grids, in three-dimensional grids, okay? So we cannot represent, I mean, of course, if we want to represent the reality, we should increase the size of the delta x, delta y, of the computational grid, okay? So we should reduce as much as possible this grid here. But of course, if you reduce the size, so you use finer grids, you will have a lot of more points where to solve your equation, which of course will need more computational power. So what people say is that, okay, we have to understand that all this part here is related to average value. Okay, so I'm solving here, my computer, my code says the mean of the velocity here is u bar. What about u prime? U prime is important because if you look at the equation, it is related to this term here, this and this, okay? So that's why the effect of the turbulence scales, which are also called sub-grid scales, is important, okay? So when people started to create a global model of the atmosphere or global model of the ocean, they had to cope to the fact that mesoscale, as you remember, has a dimension of about 50 kilometers in the ocean and let's say 500 kilometers in the atmosphere. Okay? So since mesoscale is the most energetic part of the entire energy spectrum in the ocean and in the atmosphere, it's important to solve this scale, because otherwise you completely fail to represent the general circulation and so on. So if I have grids about, let's say, 100 of kilometers, so if this delta x is 100 kilometers, I have 5 points to represent one, for example, one cyclone, okay? You can understand that in the ocean is much more difficult because you need 1 order of magnitude more. But in any case, what happened within the cyclone? So what is happening at scales smaller than 100 kilometers? So this is related to the turbulence, okay? And turbulence, actually, the effect of turbulence is described in this equation by the eddy terms. And there are different kind of parameterization. That's why people call subgrid parameterization. That can be used, and you can work for years on finding the best subgrid parameterization. Of course, the ideal will be to have simulation which goes down to the smallest scale, but it's, for the moment it's extremely difficult. Okay, good. So 5 equations, 5 variables: u, v, w, rho, and p. F is the Coriolis parameter. Rho, 0, and g are constant. Of course, here we have the other constant, and the two, let's say, model for eddy and eddy viscosity and eddy diffusivity. Okay, so one thing more is to have a look again to our equations and take, for example, the x momentum. So if I want now to again express the scale analysis, so I will have u over t, then I will have u squared over L, again u squared over L, w u over h omega u, p rho 0 L, and then u h squared. Okay, as I said before, the rotation is the most important player in GFD. So let's look what happens if we if we compare each of these terms with the Coriolis term. So it means I will multiply each of these terms by 1 over omega u. So here I will have 1 over omega t. Here I will have u over omega L, the same. Here w over L omega h. This will be 1. This will be p rho 0 L omega u, and this will be nu over h squared omega. So all of these are a dimensional number. So now we can define the most important adimensional number in GFD. The first one is called the Rossby temporal number. Each adimensional number is bears a name of a famous scientist who make a lot of work in GFD, and it's written with the capital. First, the initial is capital, and the second one is lowercase. Okay, so the temporal Rossby number is practically the ratio between the local variation of horizontal velocity with respect to Coriolis. Okay, this is the Rossby number. Rossby number, which of course is the same in the two horizontal terms of advection, is the ratio between the horizontal advection and the Coriolis term. This will be, we'll look later. This practically will give us a scale for the dynamic pressure, okay, which is rho 0 L omega u. If all these terms here, for example, are much smaller than 1, okay, so I just take a balance of this and this, I can extract a scale for P, okay, because I have one order of this one. So it means that P has this scale here. And finally, this one is called the Acma number, which I told you before. Acma number is the ratio between the vertical friction and the Coriolis term. Okay, so the last term which remain, so we can rewrite it and multiply this by. So we can have omega h multiply by u over u and n over n. So I multiply and divide it by u and by l. So I have WL over UH, WL UH, and then U over omega L. Okay? So this is again the Rossby number, and this is what we said at the beginning, which is W over H over U over L, which is actually the ratio between the vertical divergence or convergence and the horizontal divergence or convergence multiplied by the Rossby number. Okay? So this term is a little bit complicated, but actually it tells us that the ratio between the vertical term of advection with respect to the Coriolis term scales as the ratio between the vertical and horizontal divergence multiplied by the Rossby. So it's very close to the Rossby number, okay? According to the fact that this can be, as we said before, about 1, order than 1, if we have a three-dimensional convergence or divergence, or much smaller than 1. Okay, so there is also another number which maybe those of you who worked with fluid dynamics can remember. So, any of you remember which is the most important dimensional number in fluid dynamics? The Reynolds number. So Reynolds numbers, Reynolds is the same as before. Osborne, Reynolds, always him. A lot of big men in fluid dynamics. So the Reynolds number is actually the ratio between advection and advection and horizontal diffusion. So it is written as U over L over nu. So if we play a little bit with this one, we will find that this can be written also as the ratio between Rossby and Acma multiplied by L over H squared. Okay, so you can do this by exercise. So since L is much larger than H, this term here, of course, is much larger than 1. Since these two terms can be mostly of the same order, we can consider this as a sort of number which does not affect too much this term here, and so we can say that Reynolds number in GFD for our hypothesis is much larger. That's why we say that GFD flows are turbulent. And this is sort of a justification of the fact that we no longer use the molecular constant, but we use the eddy function. Okay, because don't forget, eddy diffusivity and eddy viscosity are properties of the flow, not of the fluid, and are function, as for example in this case. Okay, so yes, we can also do. There is one final number. So you remember that Rossby number is exactly the number that we find in the U we found in the first lesson. We call it this one was small omega and this was epsilon. Okay, there was another which was sigma, which was related to the ratio between potential and kinetic energy. So there is one still term to analyze, which is the pressure. So if we actually make so we have the pressure expressed like that in our x and y component of the momentum, and then we have 0 equal and then we have the z momentum, which is this one. Okay, so this scale has p over h and rho g, okay, or delta rho as well. Okay, so we can try to make the so this means that p, if we neglect everything, will scale as rho 0 L omega u, and this, which will tell you from the bottom that p will scale as delta rho g over h. Okay? So now we are considering the fact that we have a variation in density, okay, in the most general case, and we will have a sort of a stratification. So our fluid is in most generally stratified. So if we take the ratio between the two terms, we have delta rho gh over rho 0 L omega u. So we multiply up and down by u, and so we have u over omega L, so u omega L, and then we have delta rho gh over rho 0 u squared. Do you remember? This is exactly the scale between the potential energy. U now is potential energy. Sometimes it's a little bit funny to use the same, and the kinetic energy. Okay, so this is actually 1 over the sigma that we used on Monday. So this number here is well known again from another scientist, which is Richardson. Okay, so Richardson number makes the ratio between the potential energy related to the variation of density and the kinetic energy related to the fluid flow. So we can say that this the ratio between the two expressions of pressure scales like the Rossby number multiplied by Richardson. Okay? So it means that according to the importance of these different numbers, so you can really tune the number and have different kind of flows. Okay? So one of the first, or much better, the second, let's say, kind of flow that we can analyze is the one which just consider the balance between Coriolis force and gradient of pressure. Okay? So we are considering a flow where the temporal Rossby number, the Rossby number, and the Acma number are much smaller than 1. What does it mean? It means that since this is 1 over omega t, much smaller than 1, it means that the time scale of the flow I'm studying is much slower, much longer than the time scale of the rotation, than 24 hours. This one says that the frequency of oscillation, we can call them frequency of oscillation, but the frequency of the flow I'm studying is much smaller than the frequency of the rotation of the Earth. And that, the last one means that we are actually far from boundary. Okay? So we are completely neglecting any kind of effect due to boundary. So we can say that we are going to describe the effect that we can observe, for example, quite high in the atmosphere or quite deep in the ocean. Okay, so we are far from the boundary, far from the surface, far from the bottom. We are looking at very slow motions, okay, with the time scale larger than 1 day, and with also advection terms which are much smaller than or advection acceleration, they are much smaller than the Coriolis acceleration. So if we look at our equation, 1, 2, 3, and 4, and 5 can be neglected. So we obtain very simple form and I will say something more. I will also take homogeneous fluid. Okay? So it means that I don't want to have any kind of buoyancy effect. So rho, which is the perturbation, remember that we have a prime here, is equal to 0. So the buoyancy term rho g can be neglected. Then we have the continuity equation, and then for the moment we, of course, energy equation is 0 because rho is equal to 0. Okay? So energy is conserved.
So the rho here is rho prime?
Yes, we said before that from one moment, since we don't want to have any kind of confusion, initially we wrote rho equal rho 0 plus rho prime, then we substituted everywhere these two terms, and so we can say, okay, now leave out our prime, don't make too confusion. We know that when we have rho, is actually the density variation, okay? Okay, so let's say, slowly fluid, far from the boundary, homogeneous. Okay? Only 4 equations remained, and very easy to be solved. Why? Because if we impose our gradient of pressure, okay, so we know we can define our pressure, so we will have P, which in the most general case will be a function of x and y, no longer of z, because you can see from here that pressure does not depend on the vertical. So pressure can be only changing along the horizontal plane. So if we apply to the 2 horizontal components the derivative over z, so the question is, how does this flow change in the vertical? So f is the Coriolis parameter. So actually, the only dependency is on on phi, which is the latitude, which is practically y, okay? Because latitude change on the northward direction. Okay, so if we apply the vertical derivative, what we will have is that minus f dz v is equal to 1 over rho 0 dz dxp. And the second one is f dzu is equal to minus over rho 0 dz dy. So you know quite well that we can exchange the order of derivation. So what happens is that we can make first the derivative over z, but the derivative over z is 0. Wow, this is a big result. So we have obtained that with this hypothesis, our flow has no shear. No shear. So it means that when we make the consideration before of the wind and so again we have our trees, we have our wind here, and then here we suppose to have wind equal to 0, or in any case it will decrease. Okay? Think about if you are like on a tower and you can feel very strong wind with respect to what you have in on the ground. So this is not the case for this kind of flow. These kind of flows are this. Okay? So the value of u when we fix a position x and y is the same along the vertical direction. What happened? It happened that close to the ground we have what is called slip. So we are allowing to the flow actually to slip over the boundary. Okay? So it is not the usual, this is the no slip, which is of course much more realistic. Okay? But what we said that in some sense we are looking here, not here. Okay, so we are taking as an hypothesis that Acma number is much smaller than 1. So it means that we are far from the boundary. Okay, so we can consider that there will be a very small layer where we expect that this value actually will go to 0. But this is not the case now in this moment. In this moment, we are looking here, okay? We can consider the slip, and we will see a special case of slipping condition. Or we just represent, we just consider that we are taking as, let's say, closer point, as a point closer to the boundary, a point which is above this boundary layer, which we will call Acma boundary layer, and we will see it tomorrow, I think. Okay? So, this is one first important property of these flows. Another property, very, very important, is also related to the fact that we can simply solve this, this system. So if we look only to this system, which is actually satisfied because we have two equations in two unknowns, if we consider P as a parameter, as external parameter, we can solve U as 1 over rho 0 f dy dp, and V as 1 over rho 0 f dxp. And if we take the vector U, which is based, of course, composed by U and V in the two horizontal, and the gradient of pressure, which is composed by the xp and the yp, and we make the scalar product, we will see that it is 0. Okay, so you can also make this as an exercise. So just take this, multiply by the xp, take this, multiply by the yp, and you will find, because of the minus which is here, you will find that this is 0. So what does it mean? It means that the velocity is perpendicular to the gradient of pressure. So this is another interesting aspect which is proper of the rotating fluid. Why? Because if you consider a usual non-rotating fluid, so you have a U-tube, for example this one. So here we will have a sort of a certain pressure, here we will have another pressure. So of course what happens is that the gradient of pressure, if here we have P1, which is much larger than P2, for example, will go in this direction, okay? Towards the larger values. And of course, the flow will be in this direction, okay? So, U-tube is easy, okay? So, if you solve this by using the fluid dynamics, you will find this solution. So, it means that pressure and flow are always parallel in fluid dynamics. When we are in geophysical fluid dynamics, they are completely normal. So it means that if I have lines of equal pressure, which are called isobars, and here we have a high pressure center. So if we have in the northern hemisphere, okay, so when F is positive, we will have that U will be always perpendicular to the pressure gradient, which is always pointing towards the center of the high pressure. Now, don't look at this, but look at this, which is much better. Okay? So, northern hemisphere, high pressure, P equal to P1, P equal to P2, which is larger than P1, and then increasing, the gradient of pressure is pointing toward the high values, and the velocity is rotating clockwise around the high pressure. Okay? On the other side, if we have a low pressure, the velocity will turn anti-clockwise in the northern hemisphere. This is a picture taken from a cyclone over the Iceland, which is this one, and which goes spiraling in anti-clockwise direction. So these kind of flows are called geostrophic. Okay, so geostrophic flow after the first example of the inertial oscillation that we saw yesterday, which is the easiest, where you only have acceleration and Coriolis, you don't have any other acceleration, no pressure, no density, no advection, nothing, which is simply solved with the circles, no? With a specific period of oscillation. The geostrophic flow is the second model that we can have, which is quite often observed on our planet. Okay, so we can say that all geostrophic flows are isobaric because they follows the isobar. And another interesting thing is that if we consider so we make a slightly more stringent approximation. So we say that the variation of the Coriolis force over y is 0. So it means that if we are considering our Earth, so this is the equator, this is the North Pole, this is the South Pole. So we are considering to take a meridional extent of our system where f is more or less constant, okay? So if this is the case, we can calculate the divergence, the horizontal divergence of our geostrophic flow. So here it's easy because the x, the u, we will have only minus 1 over 0 f, the x, y, p. And here, since we have said that the variation of f with respect to y is tends to 0, we can also do the same, and we will have 1 over 0 f, the x, y, p, and it's equal to 0. Okay? So what I did, I just calculated the horizontal divergence of the horizontal component of the fluid. Okay? So just calculating, in some sense, I am calculating this one. Okay? So if you want, you can just put your calculation and in the continuity equation. Okay? So continuity equation, I include the u and v. I impose no variation of f along the northward direction. And what happened is that this is equal to 0. Okay? So it means that geostrophic flow on the f-plane, how people call this expression, so f-planes means that the Coriolis parameter doesn't change too much along the meridional direction. We also have that the variation in z of the vertical velocity is equal to 0, and the flow are completely divergence-free. Okay? So we can say that geostrophic flow on the f-plane are non-divergent. Okay? Because the horizontal divergence is equal to 0, thanks to the hypothesis of this of the F-plane. So it means that we will have flows that goes in this direction. We will never have any kind of divergence, like what you can have here. So this is a map of the pressure at 500 millibars. So 500 millibars is a pressure level which is about 5,000 meters, okay, 5 kilometers. So half of the troposphere, okay? So it means that if this is the surface, this is 10 kilometers, we are looking here, okay? So it's at the middle of the troposphere, so it means which is quite far from the boundaries, the top and the bottom boundaries. So Acma smaller than 1 is 0. Okay, we can consider it as a homogeneous. It's a little bit strong, but we can do it. And we can consider that since these are very slow flow which persist for more than 1 day, also the Rossby numbers are satisfied. So this is a meteorological example showing the high degree of parallelism between wind velocities, u, and pressure contours. So this is an example of geostrophic balance. Of course it is not perfect, sure. This is mathematical aspect, this is the reality, but we can say that we can have a flow which is non-divergent and which have only areas of high pressure and low pressure, and where here in the northern hemisphere is flowing with the low pressure on the left and high pressure on the right, always, okay? Another example on the ocean is the Gulf Stream, or as they call here, the AMOC, the Atlantic Meridional Ocean Circulation. Even if here the hypothesis of homogeneous fluid is very, very, let's say, too much straight. But in any case, we can consider for specific condition that the Gulf Stream is flowing and can be considered as a geostrophic, let's say, geostrophic balance. Okay. Well, good. I think we did enough for today, and tomorrow we will see what will happen if we add a bottom